Hello, in today's video I'm gonna explain a little bit in details logarithmic inequalities, and I will explain the fact and why we have to keep in mind what is the value of the base of logarithmic function or functions which are given in the inequalities, and why we have to keep this in mind. It is because for depending on the base, on the value of the base, the function logarithm base a of x can be increasing or decreasing. And based on this information, then in a couple of inequalities we have to change the inequality sign like to the opposite one. And let me now just explain why and how it basically works. So if you have a look on the definition, it is probably well known that if the base is from the set of all positive real numbers, and if a is greater than 1, the logarithmic function is increasing. Now, what is important is to realize that if the function is increasing, then for each two x's, like in this case x1 and x2, from the domain of the function, which in this case are again all positive real numbers, it applies if x1 is less than x2, then the value of the function of x1 is less than the value of the function for x2, which means basically, and I want to explain this on the graph, and in this case let me take the function which is defined by the equation y equals log base 2 of x. And if you have a look on the graph of this function and you really think about this definition of the increasing function, it simply says if you take any x, for example, let's take x equals 1, and this is like our x1, and you take, for example, x2 being positive 2, and you find the values of this function. So the value of the first x is equal to 0, and the value for x being 2 is equal to 1, and as you can now really see very clearly, 1 is less than 2, and the same applies for the value of the function of 1, which is definitely less than the value of the function for number 2. Okay, and this must apply for all x's, but if you have a look on the graph of this function, we can also take x1 being number 4, and the value of the function is in this case equal to, and if you take, for example, x2 being number 7, and you have a look on the value of this function, you can again say very easily that 4 is less than 7, and the same applies for the values of the function for 4 and the value of the function at 7. Okay, so this is the concept to understand. And on the other side, let me just explain very quickly that if we have the base of the logarithmic function, again, we know already that these are all the positive real numbers, but if the base is less than 1, then logarithmic function is really decreasing. And from the definition of the decreasing function, we know that then applies for each x1 and x2 from the domain, in this case the set of all positive real numbers. If x1 is less than x2, then the value of the function at x1 is greater. And this is something which is really opposite. For increasing and decreasing function, the value is now greater than the value of the function at x2. Let me again explain it on the example and show you what this means and why we have to understand the logic here before we start solving any logarithmic inequalities. So now in this case, let me take the graph of the function which is given by the equation y equals log base 0.2, which is of course less than 1 of x. And as you can see, the red line here represents the graph of the function, and the same procedure applies like it applied on the function before, but in this case the function is really decreasing. And if you think about, for example, x1 being number 1 and x2 being again number 2, you can very easily see that the value of the function at 1 is really greater than the value of the function at 2. So basically 1 is less than 2, but the value of the function at 1 is greater than the value of the function at 2. Okay, and again, for example, we can take another point. Let me just take, I don't know what the value is here, but let's take and let's consider this one as being 0.5, which is less than, let's take number 5 in this case. And again, you can see that the value of the function at 0.5 is even positive number, and the value of the function at 5, you can see very clearly it's a negative number. So 0.5 is less than 5, but on the other side the value of the function at 0.5 is greater than the value of the function at 5. So this is like really very important concept to understand, because and I will try to explain or stress again this fact when we'll be solving in this case these two very simple logarithmic inequalities. And I'm pretty sure a lot of you can remember this fact, because this fact applies also when we talk about the exponential inequalities. Okay, but this is not our topic for today, so let's try to solve first these two very simple inequalities. Before I'll start, I will rearrange my screen. Okay, I will take these two inequalities for later on. And let me start with the first inequality, which is like really very simple. The next thing you have to realize before you start solving any logarithmic inequalities is to find the domain for this inequality, which basically means you have to find the domain for all the functions which are in the inequality. So this is our first function in the first inequality, and we know that the domain of this function is for all arguments, and in this case argument is everything in the parentheses here, and it must be true that 2x take away 7 is greater than 0. Okay, so basically the domain of this function says that x must be greater than 7 over 2. Okay, you will see why this is important when I'll solve the inequality. So now, as we have, we will use this fact here. The function, the base is equal to 5, so our function is increasing, and a good manner now is to rearrange the right side of the inequality, though maybe you can see it, so that we have logarithms on both sides, on the left and on the right side. So we can simply rewrite our inequality into this form, which is less than, and we need to have here logarithm base 5 of which number is equal to 2. And the answer is really quite simple, and you can think about it this way. So 5 squared is equal to number we are looking for, so logarithm base 5 of 25 is equal to 2. Now, as we have the same basis and we can say that our functions on the left and on the right side are increasing, we use this fact, okay, or this rule. So now it must be true that the argument of our function on the left side, which is 2x minus 7, must be less than 25. And now we have really like very simple inequality. And the solution of this inequality is 2x is less than 32. Now we do multiply both sides by 1 over 2, and it means x is less than 16. Okay, this would be the solution if we are solving this inequality, but as we are looking for the solution of the logarithmic inequality, and we know there is a restriction because of the domain of the function on the left side, we have to consider these two facts and put them like in one fact, which means that, and if you need to, you still can sketch the number line and represents the results like this. X is greater than 7 over 2, which is somewhere here on the number line. It is excluded, and x must be less than 16, which is for example here. This is now number 16. So the first inequality says these are my solutions, and the second inequality says these are my solutions. So if we do find the intersect, so these are the only numbers which are valid and can be the solution of the inequality. So the set of the solutions is interval from open interval from 7 over 2 till or to 16 open interval, because here we have the direct inequality sign, and this is it. This is our solution of the inequality. So if we take any x from this interval, we will get the true statement. Okay, let's have a look on the second inequality. In this case, there is nothing to be rearranged very strictly, but as we said, the first thing we have to find the domain of both functions, the function on the left side and the function on the right side, which says that the argument of the first function must be greater than 0, and the argument of the function on the right side must be also greater than 0. Otherwise, the functions wouldn't be defined, and the domain of our inequality is like this. So it means x is greater than negative 3, and x is less than 15 over 2. Okay, so these are my conditions. Now, as we have the same basis of the logarithms on the right and left side, we can simply use again the fact, but before this fact here, and I'm now in this part because, as we can see, the base of our logarithms is less than 1. Okay, so it basically means if the value of the first function is less than the value of the second function, then the arguments are on the opposite. Okay, so it means this inequality can be rewritten as 3 plus x is greater than 15 take away 2x. So please note again here, this inequality sign is changed to the opposite one. So we now solve this inequality, which is 3x is greater than 12, which means x, we do multiply by 1 over 3, x is greater than 4. Okay, now we have to keep in mind that this is the solution of this inequality, but as we are solving this inequality, we have to keep in mind that these two conditions must be met also, and also of course the condition for the solutions. So again, if you have a look on these three inequalities, it's quite helpful to sketch the number line. Negative 3 is here, Then we have like number 4, for example, here, and here we have 15/2 because it's something like 7.5. Okay, it doesn't matter if you really sketch the number line like precisely, because we are now just looking for the intersection or intercept of these three intervals. The first says that x must be greater than 4, which means these are all numbers on the right or from the 4. The next inequality, which is this one, says that x must be greater than -3, so these are my numbers. And the last inequality, which is this one, says that x must be less than 15/2. So basically this is my representation, and now I'm looking for the common numbers which meet all these three conditions, and these are numbers only from the interval from 4 to 15/2. So the set of my solutions is opened interval from 4 to 15/2. Okay, so just quick summarization here. You really, before you start solving logarithmic inequalities, you have to think about the value of the basis. If the basis, or we are now solving the inequalities with the same basis, so the only thing you think about is if the base or the number base is greater than 1, then the inequality sign remains, and on the other side, if the base is less than 1, but be careful, greater than 0, because it must be positive real number, then the function is increasing and the inequality sign will change to the opposite one. Okay, so this was like very basic concept and very simple inequalities. Let's have a look on these two inequalities now, where they are of course not like very hard to solve, but they are a little bit more complex, and the second one, or the last one, this inequality will be solved by the substitution method, and you will see later on why and how. Okay, so if we have a look on this inequality here, now the first thing we have to do is to find the domain of 1, 2, 3 and 4 functions. So the argument of the first function x plus 2 must be greater than 0, the argument of the second function x minus 3 must be greater than 0, and x plus 4 must be greater than 0, and x take away 1 must be greater than 0. From the first inequality, x must be greater than -2. From the second inequality, x must be greater than 3. The last but not least, x must be greater than -4. And the last, x must be greater than 1. Now maybe it's a good idea to have a look on all of these inequalities and to find the intercept with for all of them, which basically means that x must be greater than 3 is our condition, which basically means that x is from the interval from 3 to the infinity. So this is gonna be used when the inequality is solved. Okay, what is now important here is to rearrange our inequality so that we will have like log of something is less or equal to log of something on the right side. Now for this we will use the laws of logarithms, which means if we have the subtraction here, this means it's gonna be like quotient, so this can be simplified as logarithm base 1/2 of expression x plus 2 over x minus 3 is less than or equal to log base 1/2 of the expression x plus 4 over x take away 1. Now, as you can see, we have the logs. on both sides. So we again use the fact that these the values of these functions can be rewritten as the arguments of these functions, but again we have to keep in mind that the base is less than 1, so our inequality will be like x plus 2 over x minus 3 is greater or equal to x plus 4 over x minus 1. Now, sometimes some people do like multiply this, but we already know that the best manner is to compare any rational expressions with 0. So we will rearrange our inequality like x plus 2 over x minus 3, take away x plus 4 over x minus 1 is greater or equal to 0. Now, okay, just let me. Now we will find the common denominator, which is, and in this case, and you should probably already know why this is a good idea, we will remain with the multiplication of these two expressions, and the numerator will become like x plus 2 times x minus 1, take away, I will leave the parentheses here, x plus 4 times x minus 3 is greater or equal to 0. If you would simplify the numerator, you will find out by your own, I'm not gonna do this because of time, you will find that the numerator value is 10 over, and here we will remain with x minus 3 times x minus 1 is greater or equal to 0. Now, to solve this inequality, it's really simple, because we know that any fraction is greater or equal to 0 if and only if the numerator is positive and the denominator is positive number, or the numerator is negative number as well as the denominator. So if these two cases will happen, then we can simply say that the division or the division is a positive number. As you can see, this is very simple, because this case will not happen anymore anytime, because we have positive numerator. So we have to find out when the denominator is a positive number. For this, you should already know that this represents the quadratic function, and the roots of my quadratic function are positive 3 and positive 1, which means that our parabola of the function will look like this. This is number 1, this is number 3, and the parabola goes this way, because coefficient a in front of the quadratic term is equal to 1, which is positive number, so parabola is convex, or if you want to, it opens up. And on this interval, all the values of the function are positive, on this interval also, and here all the values are negative numbers. So we can simply say that the solution of this inequality, okay, is for x's from the interval from negative infinity to number 1, excluded, okay. Why? Because excluded, because it cannot be equal to 1, otherwise this expression would be 0, and then the whole fraction is not defined. Union from 3 to the infinity. So this is the solution, but be careful, not of our given inequality, which is this one, because now we have to keep in mind again this fact that the domain of this inequality is for x's being greater than 3. So we put these two information together, and the set of our solutions is the interval from 3 to the infinity. Okay. Now let me just also solve the last one, which is gonna be a little bit complex, because a lot of numbers and a lot of procedures to be taken, but I think we can do it, so let's do it. It's gonna be quick, I guess, I hope, I wish. And you can still stop the video and think about it. Now, what I want to say here, the easiest way how to solve this is to use the substitution, but before we start we need to define the domain of this inequality, which is of course very simple. X must be greater than 0. What kind of substitution makes sense here? Substitution. So for example, let's say u is equal, u is equal log x. Okay, so now our inequality will be like u squared over 2 plus u is less than 1. But now I have just started to think about one very important thing which I didn't say, and this important thing is that this expression is defined, as this is the fraction, it is defined if and only if 2 plus log x is not equal to 0. So we have to solve very simple equation, logarithmic equation, like this one. So log x must be equal or is not equal to -2, and we already know that the base of our logarithm is 10, so 10 to the power of -2 is equal to x, so x cannot be equal to 10 to the negative power of 2, which is equal to 1 over 100. Okay, this is also very important condition, and I really forget it, I just realized when I started to solve this inequality. So let's go back to our inequality, which means we again cannot simply do a multiplication by the expression 2 plus u, because we never know when this expression is less than 0, and if it would be, then the sign of the inequality must change to the opposite one. So this is like really forbidden. Okay, so you don't do this anytime, never ever. The only thing we can do now is to compare it with the 0, so u squared over 2 plus u, take away 1, must be less than 0, and it's gonna be the inequality, we find the common denominator, which is 2 plus u, so it's gonna be u squared, take away 2, take away u, must be less than 0. Okay, to solve this inequality you have to find 0 points for the quadratic equation u squared take away u take away 2 is equal to 0, and this is if and only if u1 is equal to is equal to 2, or u is equal to -1. How to do it, I'm not gonna explain it, you have seen this like a lot of times, so that's it. And the second thing is that 2 plus u must be equal to 0, and this is if and only if u is equal to -2. Why these points are important, you already know, because we are now looking for the case if the numerator is negative and the new denominator is positive, or the numerator is positive and the denominator is negative number, then the fraction is definitely gonna be less than 0. So, and we found this information, so now we will solve this inequality by using the table. And if you have a look on these 0 points, you can clearly understand that we will have to solve these on the intervals like -∞ to -2, As we have strict inequality, all the intervals can remain opened. So from -2 to -1, then we have -1 to 2, and the last interval is from 2 to the infinity. The first expression will be looking for positivity or negativity, is the expression from the denominator, so 2 plus u, and then we will do the same for the expression in the numerator, so it is u squared, take away u, take away 2. Let me just do it this way. So as you already know, the function u plus 2 is represented as a line which passes through the -2. This is our 0 point here. So all the values on the right side from -2 of the function are positive, on the left side they are negative. So it's or you can take any number from all of these intervals and check by your own, but I prefer to do it like graphically. So here my function is negative, all the values for my function are negative, here positive and positive and positive. And we already know that the graph of the quadratic function given here, these are my 0 points or the intercepts with the x-axis or the roots of this quadratic equation, and this is -1, oops, sorry, this is -1 and this is +2. My parabola is convex, so it opens up, and it doesn't matter where the vertex is. What I'm looking for is for this information. Here the values are positive, here the values are negative, and here also the values are positive. So I can write very easily, here comes positive sign, here comes the positive sign, negative sign, and positive sign. And now if we think about it in this concept, it means that the fraction in this case is going to be negative number, in this case positive number, in this case negative number, and in this case positive number. So the solution for this inequality for u's says that u is from the interval -infinity to -2 union -1 to 2. Okay, but as we are solving this super special logarithmic inequality, we have to come back to the substitution. So I will take this. Okay, let me just take this whole part and let me put it here, so that we will come back to what is needed. So now we are looking for all the x's, and we know that x must be greater than 0. Okay, so we will see what will happen. The only thing, if we want to find all the x's here from u, we have to come back to the substitution, and we have to do the substitution. Now for which points? For all these 3 points, 1, 2 and 3 points. So we have to solve the equation -2 is equal to log x. Okay, which means this is if and only if x is equal to 10 to the power of -2, which is equal to 1 over 100. The next point is -1 is equal to log x. This is if x is equal to 10 to the power of -1, which is 1 over 10. And the last one, 2, is equal to log x, which is then if x is equal to 10 squared, which is of course 100. So based on this information and on this information, and be careful, based on this information that x must be greater than 0, we now can write and find the conclusion. The set of roots, or x, must be from the interval 0 to, now, -2, but what is the x for -2? This is 1 over 100, so it's gonna be from 0 to 1 over 100 union. Now -1, which is 1 over 10, so it's gonna be from 1 over 10 to, which is 100. Okay, good. And this is it. If you take any x's from this given interval, in our intervals, you will find that our inequality which we were solving, which is this one, is really true. Okay, I think that's all, but just let me summarize very quickly. So when solving such an inequality, you can, with spending more time over the mathematics, can see very easily that to solve such an inequality, the best manner or the best way how to do it is to use the substitution, because then you will come to very simple quadratic inequality, and as you can see, then everything is very simple, and you should be really familiar with this, how to solve this inequality. Which in this case is by using the properties of the quadratic function, in this case linear function. You find the solution for, let me just show you, for this inequality, but as you were using the substitution, you have to do the resubstitution and find the values not for u but for x. And to do so, you simply solve this, in this case, these three simple logarithmic equations. You will find the values. The next thing you have to consider or keep in mind is the condition that x must be greater than 0. I didn't say or use this fact because this is quite clear, as our inequality is like direct inequality. Which means this number won't be included in the solution. If it would be, then you have to avoid this number from the intervals. Okay, guys, I hope this helped, and enjoy, and see you and hear you during our next video. Bye.